So now that we've done a discussion about what a hypothesis test is, let's look at a hypothesis test for very specific parameters. So the first parameter we'll look at is the population proportion parameter. And so we want to talk about what are the steps of the hypothesis test. And we talked about that in a different video, but this video will just kind of show you what those are. The first step of every hypothesis test should be to make sure your reader knows and you know what it is that you're measuring and trying to estimate or make a decision about. So you want to actually say that your random variable is something. We usually use X for random variable. You can use anything you want. And the random variable is going to be the number of success in a population proportion, number of successes. So remember to put the word number of in front of it. If you just put success, you don't know what it is. So if you just say it's the number of people who want to legalize marijuana, then you have the number of. But if you just say legalize marijuana, I don't know what that means. So it's good to actually put the word number of in front of all these. The other thing is your population proportion. Usually we use P for that. And it would be the proportion of successes. So whatever your success is, you wouldn't use the word successes here. You'd use whatever it is for your case. This is just in general to show what it looks like. Then we can get to our hypotheses. And the hypotheses are where we use the null hypothesis and the alternative hypothesis. So let's start with the alternative hypothesis. It's usually where I start, is with that. We write HA for alternative hypothesis, and it's going to be something about what the proportion is. So I realize I'm going to write this because it's a bit hard to write these with typing. You can do it, but it's just harder here. So we're going to start with our HA. And HA is going to be your proportion, that parameter. Remember, we don't know what this proportion is. We're trying to make a decision about it. We don't know what that value is. So the best we can write is proportion is equal to some, is not equal to some number. That would be if you want to show they're different. So you use not equal to if they're different. You use greater than if you think the proportion is going to be greater than some value, or you use less than if you think it's going to be less than some value. So those are your different choices of HA. This just depends on which choices you're going to do. Your HO is always going to be equal. So here your proportion is equal to that known value. P0 is your known value. And again, we use the not equal to when we're doing different. We're doing, of course, the greater than if we say greater. And we use the less than if we say less. And then you also usually state your alpha level, which is your level of significance. So you'd label that here also. All right, so then once we've done that, I made the comment that every hypothesis has certain assumptions that have to be true. These are requirements or assumptions, whatever way you want to talk about it, that must be true in order to have the results of the hypothesis test to be true. To be valid, I should say, not necessarily true, but just be valid. So let's start off with what we would state. The very first one we'd state is that you have a random sample of n qualitative variables. So actually what I should say is you have a random sample of a qualitative variable from n individual or measures of units of measure. So that's your stating. So that's what you start with. You start with that stating value and what that would be. So this is usually where we start. Every sample should be a random sample. We find we have better values with that. Then your next step is to check it. And this is where you would just describe your sampling method. How did you actually collect that sample? Hopefully it was a random sample. So that would be good. So that's the first assumption. By the way, that's the first assumption of every hypothesis test, is that you have a random sample of It may not be a qualitative variable because it may not be that you're doing a qualitative variable, the one you're dealing with, but that's always what it's going to be. You're going to have a random sample. For a proportion, and again, these change depending on what your variable is that you're working with, what if you're trying to do, or I should say what your parameter is that you're trying to work with. If you're dealing with proportion, then proportions come to us from binomial experiments. So you want to show that the properties of a binomial experiment have been met, or have been met. So in other words, you want to actually, that's your assumption. We are looking at proportions come to us from binomial experiments is where we're going with. It doesn't have to, and that's where the problem comes in. You could have a proportion that you're dealing with that's not from a binomial experiment, but in order to do this proportion test we're going to do, we need to have that happen. Then the check for this is to show that the 4 properties of a binomial experiment are valid. So you actually just talk about all those 4 properties and whether they're valid or not. The last one is that the sampling, and I'm going to write this one actually. The last one is that the sampling distribution of the sample proportion and the symbol for sample proportion is actually a P with a little hat on top of it, because we can't just use P because we just use P for the proportion, the population proportion. So this is the sample proportion would have a P with a little hat over top of it, is well approximated by a normal distribution. And the way you check that, the check for that is where you would actually look at your sample size, your N is your sample size, times your P. The P is from your, what you consider your proportion to be. Remember, that's kind of your P0. And that should be greater than or equal to 5. And then N times Q also should be greater than or equal to 5. And Q is 1 minus P. And so why this is it basically saying you have a large enough sample for your proportions you're dealing with. Okay. So those are your 3 assumptions for a proportion test. Again, these assumptions change depending on what your parameter is. Once we have that, we can then go through the calculations. We are going to be using RStudio for these calculations. And it's a lot easier than doing it by hand. And I will say that the proportion, the way you did it is prop.test for proportion test. So prop.test is the command. And then you type in your X value, your N value, your P equal to P0 or H0, whatever H0 says your P is equal to. So this is actually what H0 says. Not, you wouldn't actually type in H0 there, you would type in what H0 says. So whatever H0 says P is equal to, that's what you'd put there. And then you use alternative equals less or greater. And we do less if your HA is P less than P0. Use greater if your HA is P greater than P0. If you're doing the HA of P not equal to P0, which is actually the more common one we use these days, then you leave off the alternative statement. You just don't write it at all. It won't be there. Okay. I'm going to go ahead and do one, just a general one, just to kind of show you what it looks like, what your results would be. These have nothing to do with any numbers we have right now. So we do prop.test. You do want to make sure Mosaic is on. So make sure your packages, you have Mosaic on. So go through all your packages and then look for Mosaic. Make sure Mosaic has an check mark next to it. And my Mosaic is not on. So let's go ahead and turn Mosaic on. All right, so then we're going to do prop.test. And I'm just going to, again, just make up some numbers here. So let's say X, that's how many you actually observed. So this is how many successes you actually observed. Let's say that's 20. And then N is how many you actually took from. So let's say that's 100. So that's your sample size. And then let's say your HO says P is equal to 0.4. And then let's say we don't have an alternative. Let's say that this is our alternative hypothesis is not equal to, so I just leave that off. Then I just hit enter, and here's the result it would give. So I want to just show you what all these things are. The reason I did this is just to show you what all these things stand for. And go through this. But I do want to mention just a couple of things, just to make sure you all know what these are. X is how many successes you found. If you don't actually know what that is, if they didn't actually give you that, they just gave you your percent, then you just do N times your P hat. They would have given you your P hat. You just do N times P hat to find out what that is. Round it, and then your N is your sample size. All right, so then we can go ahead and paste this in. And I want to show you what these things are that it talks about. So making this a little bit bigger so you can see it. So first thing it does show you, it does show you here what you typed in. So this is what I typed in. So this is just showing you what I typed into R. Then this is the results. It does tell you it's a one sample proportion test with continuity correction. Don't worry about what that means. It just means that it's making it, it does a little bit of just a calculation to kind of say we have continuity on our graph, which we don't, but we still do that. Then the data, it actually is telling you the data is 20 out of 100. So the 20 again was what you typed in is how many you found. Out of the 100, that's your sample size. Then it gives you this thing called chi. This is actually a chi-squared. It looks like an x squared. So this thing right here, that actually is your test statistic. So this is what the calculator, this is kind of what R, actually not calculator, but what R actually calculates as being how it then goes to create your p-value. So this is known as your test statistic. It then gives you this thing called degrees of freedom. Don't worry about what that means right now, but that's what DF stands for, is degrees of freedom. Then it also gives you your p-value. This is actually the important thing we want. This is our p-value that we then compare to our alpha, our level of significance. It then tells your alternative hypothesis. This is a good thing to check to make sure you actually have this as being what HA says. So this should be the same as your HA. And so you want to make sure it actually is what your HA said. If it's not, then you typed in something wrong up here in your prop.test. And this one actually is saying true P is not equal to 0.4, and that's what we wanted. We wanted a not equal to in this case, because I didn't put an alternative equals. Then it gives you something called a 95% confidence interval. We'll talk about that later, what that means. And then it gives you a sample estimate P. This is what is your P hat. This is actually what, this is your sample proportion. And so you would just write down these three things, the test statistic, the p-value, and your sample proportion as part of your calculations. And then you can make your conclusion, and then you can make your interpretation. Remember, with your conclusion, you're going to reject HO. If your p-value is less than your alpha level. and you fail to reject HO, if your p-value is greater than or equal to your alpha. And then your interpretation, it depends on if you rejected or failed to reject. If you reject HO, then your interpretation would be there is enough evidence to support your HA. Now, don't write HA there. Write what HA said. And don't just write the symbols for HA. HA is in words. You should write in words what it says. It could have been that you thought the proportion was not 0.2 or 0.4 or whatever it was. So this is where you'd actually say that. And then if you fail to reject, then there is not enough evidence to support HA. And again, we're trying to support or not support HA. So you want that to actually be the way you write that conclusion. And that's basically the steps of your hypothesis test. Let's go ahead and do a quick example of this. Here's an example. Healthy people do all 4 of these things. They work out 4 times a week. They eat 5 to 7 servings of fruit and vegetables a day. They don't smoke, and they visit a doctor at least once a year. Now, it turns out only 4% of Americans do all these things. All 4 of these things. I happen to believe that Flagstaff, which is where I live, residents have a different proportion than most Americans. I asked 24 students in a previous class, and 3 of them do all 4 of these things. Does this provide enough evidence to support my belief? And I would like to test this at the 5% level. So we're going to go ahead and go through the steps of this. Go ahead, go through all of our steps. So that, again, the first step of every hypothesis test is to state your random variable, and parameter. And I guess I could type this because this is actually just words. So I'll type this instead of writing it so you can read a little bit better. So your random variable, again, we use X, but you can use anything you want. You can even just say RV or just write out random variable. I don't care. This is going to be the number of. And what we were measuring, this again is what we're counting. So we're counting how many Flagstaff residents, because this is what I'm caring about. I don't care about everybody else. I care about Flagstaff residents. I'm going to compare it to everybody else. But I believe Flagstaff residents have a different proportion. So therefore, I believe it's the number of Flagstaff residents who do all 4 of these things, or what we consider healthy people. Again, I don't know what this is. So when I go to write my proportion, my parameter is a proportion. And I can find that out a lot of times because right here it says the word proportion. So look for that kind of stuff. Look for where it says what that is. Because a lot of times your wording that you want to use is somewhere in this. Not always, but a lot of times it is. So look first to see what it is, and you've got that word proportion right there. So that tells you that we're dealing with proportion down here. So this would be the proportion. And now it's just the same as what you said your random variable was. Instead of having number of, it's the proportion of Flagstaff residents who are considered healthy people, because they do all 4 of those things. All right, so that's our first step of our hypothesis test, is do that. So now let's go to the second step of our hypothesis test. This is where we state our hypotheses. So again, this is where you're going to state your HO and HA. We usually put the HO first, but I usually state the HA first. So this goes back to my question. And I believe Flagstaff residents have a different, so I'm looking for that word, different. I didn't say greater than or less than, I just said different. So different would mean they're not the same. If they're not the same, then they're not equal. And I'm saying it's not equal to what most Americans are. And so then I go back to here to see what number was it that most Americans have. In this case, I happen to have a value for that. And so I can put in that the proportion is not 0.04 or 4%, but it's better to put these as decimals. Then your HO is always equal to. So once you get your HA, which is your question, your HO is just put an equal sign for it instead. Then again, like I said, it's better to put your level of significance here. And the level of significance in this problem was, we said, to test at the 5% level. So that's your level of significance, is that 5% level. All right. Okay, so now that we've stated our hypotheses, the next step is to state and check your assumptions. All right. I'm going to go ahead and type these for most of them. The first assumption is that you had a random sample. So a random sample of responses, because that actually is what I'm looking at. I didn't write down my variable. My variable, though, was responses of Flagstaff residents was taken. And I probably should go ahead and say what size it was. So random sample of, I had 24 students, so a random sample of 24 responses of Flagstaff residents was taken. So that again is my stating. So I should probably say state this. This is my stating. Now I'm going to check it. So this again would be where I would describe how I took the sample. When I go back and look at this, it says I just asked students in a previous class. So that doesn't sound like a random sample at all. So when I go to check this, I would say the sample was taken from students in a class. So it was not random. In fact, it's what is considered a convenient sample. I just happened to take the people that were close to me. So that means I have violated this assumption. I'm going to keep going, even though this assumption is not true, just because I want to keep going with this and show you the process. But realize that if this assumption is not true, first off, you have control over this. So I had control of how to take my sample. I just didn't take it correctly. So you want to make sure this is done correctly. In this case, I don't even know if I could say that this is a representative sample, because these were all college students and they might have a different ideas about exercise and eating right than everybody else. So I wouldn't even say it's representative, but we're going to go ahead and go with it just because I want to keep doing the process and show you how it works. And in fact, when you're going to do your homework, you probably want to just go ahead, even though some of the assumptions aren't true, just keep going with the process. But just realize that it may not be true. It may not be a valid test. All right, so then the second one we're going to state, and that one is that the properties of the binomial experiment have been met. So that means we have to think about what all those properties are. So then we go back to our check and we're going to look at those properties. And the first property is that we had a fixed number of trials. So what I would just probably say here is there are a fixed number of trials. Since 24 students were asked. So that one's good. The second assumption, or the second property, I should say, not assumption, but the second property is that we have the trials are independent. And the trials are independent since one student's response doesn't affect somebody else. All right. The third assumption, I'm sorry, the third property of a binomial experiment is that we have two outcomes, and we do. There are two outcomes. Either they are healthy, they are considered healthy, or not. And then the last one was that the probability of success of doing those things is the same. From trial to trial. And is that 4%. So now we can say, so the properties have been met. All right, cool. So we have that assumption, that requirement. Now we have one more requirement. So the last requirement is that the sampling distribution of p hat which is your sample proportion, is well approximated with a normal distribution. And so the way we prove that, or the way we check that, I should say, so this was the stating part. All right, so this was our stating part. And now we're going to go ahead and do the check. All right, so the check here is where we look at n times p and n times q. So the n times p would be, we had 24, and remember our HO says that p is equal to 0.04. So we are assuming HO is true for the moment. So that's why we can do all this. We're going to assume it's true. So it's 0.04. And so then we calculate what that is. And that happens to be, I'm to get my calculator up, 0.96. So we have a little bit of a problem. And then we're going to do n times q, which would be 24 times 1 minus times q, and q is 1 minus p. So it's going to be 24 times 0.96. And that's 23. I don't think this other one's right. Let me check that again. So 24 times 0.04. Yep, that is right. Okay. So we get that. So first thing I notice is that n times q is greater than or equal to 5, but this one, n times p, is not. So this may not be met. And so we aren't able to say we can definitely approximate with a normal distribution, our p hat. But again, we're going to go ahead and do the problem anyway. It's just realizing that may be the issue. All right, so now that we've done that, so we do know that some of our assumptions of the test may not be true. Some of those requirements may not be true. And so the rest of it may not be valid. But now we can go ahead and go into our next step, which our next step is to do the calculations. And so again, we're going to go into RStudio to do that. I'll bring it back and put it over here when we're done. We're going to go into RStudio to do this process. And again, we're doing a prop test. So we're doing a prop dot test because we're doing a proportion test. So proportion, prop, proportion. Our N was our X was 24. We had 24 students. No, we had 3 students times 24. So we had 3 students who did this times 24, and we're checking to see if we're close to 0.04. So I have all that, and then we had a not equal to. So we don't have to worry about putting anything else in there. We can just hit enter. And I'm going to go ahead and copy this and paste this into where we are so we can talk about it. All right, so again, what we typed in here is the 3 came from the fact that we had 3 students. So there's my X. So right there, when we talked about these 3 students, that is your X value. And then we had our 24, that's our N value. And then we are HO, we're assuming HO is true, that says it's 0.04. So that's where all that came in. So this is our X, this is our N, and this is what HO says. I didn't put in an alternative equals because our HA, in this case, was a not equal to. So since we had a not equal to, we don't need that alternative equals because R just assumes it's not equal to. And we can check all that. So here's again the output. So this is our output. And again, it's telling we did a 1 sample portion test. We have a 1 sample because we only collected 1 group of information. We weren't comparing those to another group. We were comparing it to a known number. So it's considered a 1 sample proportion. We have the 3 out of 24. That was the data we typed in. Again, that should confirm with what we typed in. And then we have, here's our chi-squared. That's our test statistic. There's our p-value. And there's our, a bit farther down, there's our p hat. All right, and then it gives us a warning thing. It does tell us that may be incorrect to use this because we actually have that same thing where we had the n times p was not big enough. So it actually is giving you that warning right there. So if you forget to check that, it'll actually give you that warning here if that's the case. So this is what this means. That right there says n times p was not greater than or equal to 5. Or n times q. In this case, n times q was. But it gives you that because one of these 2 was not true. And so that's a good check to see that you actually have that part right. So I'm going to go ahead and write these things down. My test statistic. And even though I gave you this, you should write down what these values are just so that your reader can read them. So my test statistic was 2.57. Then I have a p-value. My p-value, this one I'm actually going to write out more because this is actually, it's a pretty big number. I was thinking it was a small number, but it's not. So it's 0.01. 0.010, I think it was, or maybe 0.11. Yeah, 0.11 when we round it. All right. And then I should write down what my p hat was. That is just what we found from this sample. So from this sample, my p hat was equal to, and this just to give you an idea, of 0.125. And that you can actually calculate without having R do it for you because that's just the 3 divided by the 24. All right, so now we have our calculations. So now we're ready to do our last 2 steps. Our last 2 steps are, we have the conclusion. And our conclusion is we're going to fail to reject HO. Since your p-value is greater than 0.05, which was our level of significance. And that means that when I go to do my interpretation, which is what you're basically telling people your answer. They don't want to read, fail, to reject. So the interpretation is for your reader. There is not enough evidence to support that Flagstaff residents are healthy people, have a different proportion, I should say the way, that Flagstaff residents have a different, that are healthy people, let's do that way, considered healthy people, because they do all four of those things, is different from 0.04 or 4% if you prefer. Because that, again, was my HA. My HA was that it was different from it. So that's all I can say is that, yes, it is. We can't show it's different. And that's a hypothesis test for proportion.